Welcome to this quick introduction into continual learning in the context of reinforcement learning. A continual learning system can be defined as an adaptive algorithm capable of learning from a continuous stream of information, with such information becoming progressively available over time, where the number of tasks to be learned are not predefined. Critically, the accommodation of new information should occur without catastrophic forgetting or interference, according to Parisi et al. 2019. So, where in classical machine learning, we would want to learn a static data distribution. In continual learning, or we can characterize continual learning as learning from a dynamic data distribution. So basically, we want to learn over time and over changing input distributions. Of course, there are different types of continual learning. So for some tasks, we have maybe the same output labels or sets of output labels, but different input distributions. For others, we may have changing input distributions, but also changing labels or even completely disjunct labels. Both instances are classes of continual learning, among many others, but well, maybe it gives you a good feel for the diversity of different applications or, well, types of continual learning. As the definition already states, there's a big problem or a big difficulty in continual learning, which is catastrophic forgetting. Here, we basically learn new information and this results in forgetting old information, or heavily disrupts the basically accuracy of the model on old information. So one thing where we commonly see this is if, for example, if we have like a foundation model or a general model and now we fine-tune that to a particular task, we'll see massively decreased performance on the general tasks, whilst we see better performance obviously on the fine-tuned tasks. However, this is also true if we have completely changing input distributions. So if we train a model to classify digits, and now we stop with the digit classification and start training the model on now dogs versus cats, the model might actually pick up the whole dogs versus cats classification task faster than if we would train it from scratch, but also it would only perform very poorly on the digit classification task. And so this is the whole catastrophic forgetting problem. It's still the biggest problem in continual learning today. And it brings up this trade-off between, well, basically model stability and memory stability. So how well do we actually remember old trained information after learning new information? And plasticity, so learning plasticity, how well can the model actually pick up new information? And so ideally we want to be able to do both, but as we find, we have to engage in some kind of trade-off between stability and plasticity to avoid this problem of catastrophic forgetting. With this trade-off comes another trade-off, that between inter and intra-task generalization. So basically, we also want our model to perform very well on a given particular task, so in intra-task generalization, but then also we want it to perform well across tasks, so we have inter-task generalization. And we can basically classify the types of continual learning problems as you can see in this diagram here. So basically we have a regularization-based approach. Here we would maybe increase the stability of the model through regularization and through that try to get it to maintain or still remember old information, not to change too much. Then there's the replay-based approach, which basically just means that we feed samples from the old previously learned input distributions back into the model continually whilst we train it on new tasks, which is not ideal. It's more of a naive baseline because it's very computationally intensive. It means that we need access to the old data distributions always, which also is very storage intensive, and also it just takes longer for training to do these extra replay iterations. And it's also not really the core idea of continual learning, because as we know in humans, we have this ability to pick something up, learn something, then not think about it for maybe months or years, and then we can still do the task while we have learned like a bunch of other stuff with never repeating this, the first skill. And so this is kind of what we strive for in continual learning, which, you know, also humans learn well with repetition, of course, but yeah. Anyways, then we have also the optimization-based approach, where we try to get the continual learning method to, or like where we want to design our optimization in such a way that it particularly optimizes for retaining information while also learning the new one, which is basically we want to optimize the gradient in such a way that it works with continual learning. Then the representation-based approach is basically just how do we get, well, a robust and also well-distributed representation of our input distributions, or also our changing input distributions to achieve the continual learning goal. And then lastly, the architecture-based approach is basically how can we parameterize a model and how can we actually build the architecture of a model to make it, well, task adaptive. And yeah, that's the last approach. And now I've generally talked so far about continual learning as a whole separate thing, but now I want to put it into the context of reinforcement learning. In standard reinforcement learning, we have a basis, and we aim to build an agent that can solve problems by identifying a fixed high-quality element in this basis, as defined by Abdel et al. 2024. And so the basis is basically the set of all possible agents. And now on a fixed data input distribution, or like in a fixed environment, we now want to identify an optimal agent in this static environment. However, if we have dynamic environments or even changing environments, which is a realistic thing in real life, rarely stays the environment the same. We see that in problems in machine learning with like data drift. I mean, more generally in reinforcement learning, if or some kind of robotic instance or some agent actually behaves or interacts with the real world, which is constantly changing, yeah, this whole continual learning thing becomes relevant, because here a reinforcement learning problem is an instance of continuous reinforcement learning when all the best agents we can find are continual learning agents relative to that basis. We don't have like this fixed static best policy or best agent, but instead basically we want to design agents that continue to update and to update their behavior and search for, well, learn throughout their lifetime and throughout their experience indefinitely. So we basically want to learn forever, continually. And with this, I already want to end this video. Thanks you very much for watching, and I hope you enjoyed it.